I really appreciate you coming out for this. This is an informational meeting because the city really wants to make sure that you have all of your questions asked and answered so that you're an informed voter when you go to the polls on June 5th. This will be on the ballot, as I'm sure you all know. So please ask. We've got the experts here, the engineers, and I can say they've just done an outstanding job in putting the information together, looking at all of the options, all of the locations, everything on this entire project. You know, this started several years ago through a community survey. And we heard through the community survey that the majority of comments were that they wanted to see a water treatment plant. Well, at that time, we didn't do anything with that because we really didn't have the information to provide to the citizens on what it was, how much it was going to cost, where the location was going to be, and all of those details. Well, since that time, it's taken us this long to get everything in place, have the engineering professionals put together everything and give them time to research everything, to talk to different rural water systems as far as their capacity and being able to add on to those, and they'll be getting into that shortly. So I'm going to turn this over to AE2S, and you see Advanced Engineering and Environmental Services. They are the engineering firm that the city hired to research the water treatment plant and get all the details so we could bring it to the public and look at costs and everything that's involved in it. Like I say, I really am very pleased with the work that they did and that the information they had, and I think that through their presentation, it'll get down to the details that you're all looking for, and certainly we'll be available for questions. We'll be here as long as it takes to make sure everybody's informed. This is the third public informational meeting that the city's had. We've had two before. This will be the last one, and I'm sure Dale will cover it, but if you have additional questions after this, his presentation is on the city website. You can go out there and look at that. You can call any of the city staff, call me, and we can certainly get your questions answered between now and June 5th. So with that, I'll have Dale come up. Dale is with the engineering firm. He'll be giving the presentation. I'll let him introduce his staff that he brought along with him. So Dale, thanks again for coming.
Yeah, I just had to check in the back to make sure that they all didn't run off. I'm pleased to be here. My name's Delvin DeBoer. I'm a South Dakota native. I went to school at South Dakota State University and then taught there for quite a few years before I eventually graduated and got to do some real work in about 2012. And so this is what I love to do. I really enjoy working with systems and with communities to help them understand what the possibilities are for their future, for in this case, the future water supply for the city of Pierre. With me today is Kevin Smith. Kevin is out of the Sioux Falls office, as I am. Kevin actually is a Pierre native. Are your folks here tonight? They are. And so, yeah, and so they're just checking up on you to make sure you showed up. Kevin's the operations manager in our office and works on the financial side of things. And then also in the back is Brian Bergantine. Brian was the lead of the technical group to do the cost estimation, the assessments, and so forth. And so he basically was the technical group leader for this project. And I was fortunate enough to be the project manager. Tonight what I'd like to do, oh, by the way, can you hear me well enough? Okay, we're good. Tonight I'd just like to present the results of this study and intend for this to be a presentation, and if you'd hold your questions until the end, then we can sort of segment things that way. It'll work best for future review and things like that. So let's do it that way. We were hired to do a comprehensive water study, and when I say that, when we came on board, our idea was to develop a team. And the team wasn't just us. It was including folks from the city of Pierre to come alongside AE2S and help us understand what your concerns are and what the needs are for the future. And so most of the evaluations that I'll present tonight were vetted or discussed with the Pierre team to understand if this was the best way to go or if there's other alternatives that should be evaluated. And so I really want you to understand that this was a team effort, and the team included folks from Public Works here in Pierre. Our job was to look at the future water supply needs for Pierre. And when we think about water supply, we have to think about the source of the water, where it's coming from. We have to think about the treatment of that water, if it's necessary to treat it, and then what does that look like? And then finally, to get it into the distribution system, what improvements need to be made in order for that to happen. And so the study included source, treatment, and then distribution. That's how it's split up. Tonight we're going to focus mainly on source and treatment because that really consumed most of the effort in the study. Whenever a plan is made, you have to have an idea of how big it should be. And the size of a facility is dependent upon the number of people that are using the water or the water consumption in the community. So there has to be a planning period. In the case of this study, the planning period was 2045 as the planning date. And currently the census population is about 13,600 people. In looking at population trends of the community and of the county and so forth, it was agreed by the team to use a design population in the year 2045 of 16,100 people. At that time, the average day consumption was estimated to be 2.72 million gallons per day, with a maximum day consumption or production of 8.8 million gallons per day. There are factors that affect that maximum day. You can see that the maximum day is almost 3 times what the average day is. And the main factors that affect that would be population growth, but primarily in this community, it's the summer water use. It's the lawn watering that occurs during the summer that causes a peak demand to occur. As a part of the teamwork, we discussed, well, what can be done to try and reduce that peak day demand? And we discussed various conservation features that could happen in the community to manage the water demand. And that could be reducing that peak day anywhere between 0.5 and 1 MGD, just depending upon the policies that get put in place to manage water demand. But in the end, it was determined to design the peak demand for the water treatment plant, the peak production, to be 8.8 MGD. Okay, a part of the evaluation is also to look at the capabilities of the existing system. The city of Pierre has 12 wells that are located along the river. Well 11 is down in the southeast side of town here by itself. There's a series of wells arrayed along the shore of the river near the park system there. And then there's 4 wells out on La Framboise Island as well. These wells pump water into the lowest part of the distribution system. That's, as you drive through town, you recognize you're sort of on the low part of town. And they pump water into the Harrison and Euclid reservoir. And the water level in that reservoir sort of sets the pressure for the lowest part of town. There are pump stations at both of those reservoirs that pump water to the next pressure zone, which we call the airport pressure zone. And the water pressure in that zone is established by the water level in the reservoir at the airport location. There's a pumping station there that will pump water from there up into the highest zone, or the highest elevation of the community, whose water pressure is set by the water level in the Snake Butte Reservoir. So there's essentially 3 pressure zones in the community. One down here by the river that's pumped into by the wells. The next one between, in this area of town, that's pumped into by pumping stations at Euclid and Harrison. And then this upper pressure zone up here serving these folks up here, and also potential new customers out there that's pumped into by the airport pumping station. As we reviewed the condition of these facilities, we recognize they're generally in good condition. They've been kept well by the community with good operation and maintenance procedures. There's a couple of older reservoirs, one at Euclid and one at Harrison, that show a bit of structural age, and if they continue to be used, will likely need some rehabilitation. And then finally, there was recognition of electrical modifications that should occur at the wells to keep them up to date and enable them to continue operating into the design period if they were continuing to be used. So basically, that's the evaluation of the existing system. We're all curious about the water quality, and so we needed to summarize that as well. So here we have 4 main things I want to talk with you about. One is manganese, and the second one is hardness, the third one is sulfate, and the last one is dissolved solids. The water moves through an aquifer, and as it moves through an aquifer, it's the soil formation that will dissolve things into the water. And so calcium and magnesium, which make up hardness, dissolve from that aquifer material into the water. And as well, manganese will dissolve into the water, sulfate will dissolve. And so these things that are present in the water are as a result of the history of the water in the aquifer. All of those dissolved minerals contribute to the total dissolved solids concentration. It's just dissolved matter. If you would put that water on your stove in a I was going to say beaker, but a pan, you put it on the stove in a pan and just let it evaporate, you get a white residue at the bottom. And that residue is the dissolved solids that you've got remaining in the water. Now they've become precipitates. Okay? There is a general trend in the well system here in town to higher total dissolved solids. Wells 6, 7, and 11 have trended to the highest concentrations. And in fact, if the wells continue to be used, we would recommend that those wells be discontinued in terms of their use, and that different wells be put in place to try and replace those, because the concentrations are up in the thousands of total dissolved solids. The remaining wells are trending upward as well. In other words, the quality is getting worse, but not quite severely as wells 6, 7, and 11. And generally, the sulfate is increasing, hardness is increasing in these wells at a gentler trend, but still is increasing. And so that's the trend that we saw in looking at the well quality, and that it's just gradually getting a little bit worse as time goes on. However, there is treatment, you'll see it on the next slide, to make it so that the treated water meets the requirements of the health-based requirements of the Safe Drinking Water Act. And so by saying that, the water is safe to drink in terms of those requirements, the health-based requirements. It just has dissolved substances in it that cause it to be a little bit troublesome in some locations for use. Okay, well, what happens at the wells to make it so that it's safe to drink? There's little treatment systems provided at each well. Fluoride is added at some of the wells. The capability is there to keep a consistent fluoride concentration in the distribution system. There's a sequestering chemical to tie up the manganese and the little bit of iron that's there to try and hide its presence from the water. And so what it does is it holds it in solution for as long as it can, and then eventually as time goes on, it starts to release. And then you see the released version of that. There's chlorine that will combine with the ammonia that's present in the groundwater to form a chloramine residual, and that's the disinfectant residual in the distribution system. So before I go on, what I want to do is just show a little experiment to demonstrate, and of course you guys have seen what the water does when you spray it out onto the landscaping and so forth. You see this brown residue. If we would treat this water to remove that, we want that reaction to happen very quickly. We want to create the particles that you see inside the treatment plant and make them precipitate so that we can filter them. So we're undissolving the manganese very quickly. One of the chemicals that we would use to do that, if that would be a chosen alternative, is potassium permanganate. And so what I'm going to do is take this sample of the well water that's stirring here in my stirring plate. Looks pretty clear when you pump it. This actually was freshly pumped this afternoon. Right, Derek? So it looks pretty clear. If you would just let this set out for a day or two, it would start to turn brown. Or if you just go ahead and spray it out over a period of time, you'd see that on your sprinkler systems as well. And what I want to do is simulate what we do in a treatment plant to make that happen really quickly. So this potassium permanganate actually looks pretty nice when you put it in the water, but you see pretty quickly it's going to turn brown. And it's oxidizing the manganese. It's transforming it from a dissolved form to a particulate form. And we want that to happen just as quickly as it's happened. Actually, the manganese has already been oxidized here. And as we continue to stir it, the little particles of manganese will start to flock together to form larger particles that can be filtered out in a treatment facility. So that's how that would be removed in a water treatment plant, just like we're showing here. And by the end of this presentation, you'll see that there will be particles that you'll actually be able to see that look like they'd be filterable. Okay? Just as a matter of comparison, this is the river water, and you can see it looks clear as well. The river water is excellent quality, and we'll talk about that here in a couple of slides. If we would put that permanganate in the river water, it would stay pink because there's no manganese there to react with that chemical. So the chemical would not be consumed. It would just stay pink, and people drinking that would complain because the water is the wrong color, right? You expect it to be clear. Okay? So we talked about the treatment provided at each well. There's 3 chemicals that are added to the water. And so that's really the existing system. That's how the water is prepared in town and put out into the distribution system. Our next step was to look at different sources that could be used for the city of Pierre. Of course, you have the existing well field that's in the Missouri Aquifer. That aquifer is influenced by water levels in the river, and we think there is some recharge from the river as well. But as a result of that formation down there, manganese dissolves, and so you end up with high manganese concentrations. Also, another source might be the Missouri River itself. The city could build an intake and draw water from the river, treat it appropriately in a treatment plant, and then use that, similar to what Mid-Dakota does up north of town, or the Minnewachuny-Oglala-Sewell water supply system does north of Fort Pierre. They both use water drawn directly from the Missouri River. And so what about those regional systems? A question is there capacity available? Can they bring water to the city of Pierre? And so we talked with the managers of these facilities. One of them is the Mid-Dakota Rural Water, just northeast of town in Oglala-Sewell, north of Fort Pierre. And it turns out that the existing capacity of those systems is pretty much spoken for by the customers of those facilities. In other words, there's not excess capacity to take water from those facilities and bring it to Pierre. And so as a result of that, you just can't hook up to those systems. Pierre can't do that. There would additional construction would be needed in order to enable that to happen. And quite frankly, we price that out, and the cost of that construction is greater than the cost of the alternatives that we're presenting here today. And so, quite frankly, it didn't make sense for us to pursue that any further because of the fact that it would be even more costly than what we're talking about today. Okay? All right, so let's compare the quality of the aquifer with the river. And I've highlighted the values that we've had before on the prior slide. This manganese in the range of 2.4 to 2.5. Hardness about 245. Some of you might be familiar with grains of hardness. That's equivalent to about 20 grains of hardness. Sulfate about 360, and then dissolved solids about 850, these numbers you saw before. This would be the quality of the Missouri River treated and brought to Pierre. So if you would take that water and treat it in a water treatment plant, you'd see of the style that we're talking about in terms of the alternative, the surface water alternative in this plant. The manganese concentration would be very low, 0.03 milligrams per liter, much lower than 2.4. The hardness would be about 15 grains. It varies up and down depending upon recharge to the reservoirs. In the springtime, there's mountain snowmelt runoff that comes down through the reservoir system, and that dilutes the water concentration a little bit. Then as time goes on and that stops and you have rainfall events, there's a little bit of dilution as well. So there is a range of hardness concentrations, and historically it's about 240 to 290. And we're just saying that's about 15 grains. The sulfate will range between 200 and 300, maybe 250 is a good average of those. And the dissolved solids ranging between 480 and 620. And I think the long-term average is just over 500. So there's really a consistent water quality available from the Missouri River, from the reservoir or downstream of the reservoir. Whereas, as I mentioned before, the Missouri aquifer that you're in with your wells has a little bit of an upward trend of dissolved solids. If we would take this water either source and treat it, we need to follow the requirements of the Safe Drinking Water Act. And there's a whole list of rules here that the system needs to abide by, that they're abiding by right now. And these regulations come in two different flavors. One is a primary drinking water requirement that is a standard set to protect public health. And then there's a secondary drinking water standard that is only a recommendation. But those values affect the aesthetic quality of water, make it so it doesn't stink or look bad or have colorization and things like that. And so a system is required to meet the primary drinking water standards. And here you can see that some of them are related to the bacteriological quality of water. That's the total coliform rule. The disinfection byproduct rule deals with the consequence of disinfection. The chlorine can react with things in water to form a carcinogen. And so that's regulated as a part of this rule. The lead and copper rule influences the amount of lead or copper that could dissolve from somebody's home's plumbing, the lead solder you might have in your home, or a lead service line, or maybe the copper plumbing. Those can dissolve in an aggressive water. So the lead and copper rule is there to protect systems against that and to make it sure that a public water system doesn't produce water that's aggressive or corrosive to them. Radionuclides, really not much of an issue here in the central South Dakota. Arsenic rule. There's some other rules here dealing with organic contaminants. And then finally there's, I guess I'd call it the Unregulated Contaminant Monitoring Rule, UCMR. That is a periodic check or assessment by the EPA to enable them to explore other things that aren't regulated yet. So that's why it's called Unregulated Contaminant Monitoring Rule. It enables the EPA to require systems to collect samples on substances that aren't monitored as of now. It's unregulated, and enables them to gather data to determine whether or not there should be additional parameters regulated in the system. And there's one that I'm going to talk about on the next page that pertains to manganese that we need to be aware of. Okay, again, just to compare the river and the city of Pierre's current water against these standards. The manganese secondary standard, which is a suggestion to try and limit the amount of issues that you might see in a system for discoloration, that standard is about 0.05. And you can see that the city of Pierre's water is about 2.4 for manganese. The river water is less than the standard for manganese, the secondary standard. The sulfate secondary standard is 250. If you move into a community and you're not used to the water, and it has high sulfate in it, you can get a laxative effect for a while until you're used to the water. It's sort of like a change in your diet. You move to an area that has different water, you might not be used to it, and sulfate will cause a laxative effect. You get used to it and eventually it goes away. So they've set a suggestion for that of 250 milligrams per liter. Pierre's at 360, the river's at 230. And then the total dissolved solids, will contribute to a taste in the water. It can also cause residues to be left. I'd say an excess amount of residues to be left upon evaporation if you're washing your car. And so here their suggestion for standard is 500. City of Pierre's water currently is at 850, and the river water would be about 500, just over the standard, 520. And then just as a matter of comparison for hardness, for which there's not a secondary standard, City of Pierre water is 350, and the river water is about 250. So again, these standards are secondary standards. They're not required. They're recommended. And a community can choose to meet those standards as a possibility for water quality. It's totally up to the community. Whereas the primary standards are required and the city must meet those. Let's come back to this UCMR. It stands for the Unregulated Contaminant Monitoring Rule. And it's the fourth version of this rule. It's just coming out here. It's in the time range of 2018 to 2020, where systems under this rule will collect samples. There's about 30 parameters that systems will sample for. One of them is manganese. And so Pierre is required to comply with this rule and collect samples for the parameters that apply to them. And so they'll collect manganese samples. in this 2018 to 2020 time span. The EPA will take those data, and along with other data that is related to public health concerns related to these parameters, they'll decide whether or not to regulate that parameter. Okay? And so that data will be used to inform future regulatory actions to protect public health. So what are the questions that they're asking? Well, would that contaminant have an adverse effect on human health? Second question, is the occurrence and concentration likely to cause public health concern? And then finally, will regulation reduce the risk for public water system customers? So if high concentrations increase the risk for a public health issue, then what is necessary in terms of regulation to reduce that risk to an acceptable level? If EPA decides to regulate based upon these data, then they develop an issue of primary drinking water regulation. It's a health-related regulation. So they need more information. They have quite a bit of information about the health effects of manganese as related to inhalation, manganese-laden dust in mining environments and things like that. There's good health information related to that that says that it does cause a health problem. But there's additional information needed and being gathered by EPA to determine the health effects due to ingestion. When we drink this water, then what's the cause? It's known that manganese is essential in the diet. And as adults, we have the bodily functions capable of determining how much that is, and then our body rejects the rest. Infants have less capability to do that. So some of the concern for manganese is related to infant ingestion of manganese. But it is essential in the diet. Excessive manganese is associated with neurological impacts, brain function and so forth. And this has been demonstrated with folks been exposed to inhalation of manganese. But the verdict is still out on ingestion. And so that's the purpose of this next go-around in regulatory, I guess you call it procedure. One is to collect data on the occurrence and the extent, concentrations of this in public drinking water supplies. And then also, along with the health impacts, decide whether or not to regulate it. So that's ongoing. We feel it's important for you to understand that and to know that, because manganese is on the list. We don't know whether or not it will be regulated or not. That's up for the process to decide. In addition to that, the EPA has developed a health advisory level for manganese. They do this periodically for substances that are in the regulatory process. And so they've developed a health advisory, and there's information about that on the Pierre website. If you look at the water treatment plant section on the Pierre website, there's information about that. Their health advisory information's been out for quite a while. And so if you need more information, want to read into this more, I don't have much more time to talk about this today, but you can certainly get that information there. Okay, so here we are looking at alternatives for putting a treatment facility in Pierre. If a treatment facility is to be built, where could it go? There were 5 sites that were vetted by the team, the Pierre and AE2S team. One was up north of town, up by the firing range up there on property, I think that's owned by the city. It's very near the Snake Butte tank. It would be a great site for a surface water treatment plant, obtaining the water from the river over here. There's another site located just north of the furthest north residential area along the river. There's a little mesa up there. That's a potential site. And of course the intake then would be just down the hill, pretty steep hill, quite frankly, from there. And so that's how that site would work again for a surface water treatment alternative. And then there were 3 sites that were reviewed here in town. One is west of the Ramcota. We call it the Ramcota site, on this little green space right here. And then south of the bridge, we call this the Steamboat Park site, Site 4. There was a space potentially for a treatment plant there. And then Site 5 is a nearly bare area just south of the Discovery Center on a lot there. And quite frankly, this site was very small. and because of its smallness, would have been difficult to build a facility on, so it didn't receive a lot of favorable rankings. And as a result of the team's consideration, the focus was on sites 3 and 4. Site 3 is the the Ramkota site. Site 4 is the Steamboat Park site. And toward the end, we'll show what the size of the facility might be in the Steamboat Park site so you can get a feel for what that looks like. Both of these sites could be served by either a surface water source or a well source. And for various reasons, ranked by the team, it was determined that these would be 2 good alternative sites for treatment plant construction. Okay, so in the end, after all of this review, what would be the requirements for a treatment facility? Well, one would be that it has to meet the requirements of the Safe Drinking Water Act, the primary drinking water standards to protect the public health. The capacity of the facility must meet the design flow of the treatment that's required for the system, and that's that it has to treat water to produce 8.8 million gallons per day. And then finally, based upon public input and discussion amongst the team, it was decided that the treatment alternative must be capable of eliminating the discoloration from the water to provide a treated water manganese less than 0.05 milligrams per liter. Quite frankly, this is very common for communities like Pierre to make a choice to do this. It's pretty normal across South Dakota to remove iron and manganese from water sources that contain it. For example, Brookings has high iron and manganese in their water source, and they have an iron and manganese removal plant. Aberdeen has a well source that has iron and manganese in it, and so their treatment facility can do that. Watertown, same thing. The city of Huron is unique in that it has 2 water sources. One is the Mid-Dakota system. They got into the planning stages early on, and so they're part of the Mid-Dakota system. But they have a groundwater facility that takes water from the Warren Aquifer, and so they have a manganese and iron removal facility there. So it's very common for communities to choose to remove the iron and manganese from the water. In fact, I would say across South Dakota, it's more of the normal rather than the non-normal for a system to do that. Okay? So it was reasonable based upon your Pierre communities and the desire to remove discoloration to have the treated water manganese meet the secondary standard. Okay, given all of that, 3 different treatment alternatives were developed. One was to take the well water and remove the manganese using a process very similar to what we started here. A chemical is added to oxidize the manganese to create particles that then are removed in a filter, in a water treatment filter that's typically used for a public water supply, a granular media filter. So it would remove the brown color, but not remove any hardness or any sulfate, any total dissolved solids, mainly focused on getting rid of the discoloration, which was a requirement, right? Okay? A second alternative is to take that well water and do one additional treatment step. Run a part of it through reverse osmosis system to remove some of those dissolved solids and blend that RO treated water back in with water that has been treated for only manganese removal to achieve a water quality that matches up with the river water quality. Okay? So a little bit of hardness removed, a little bit of sulfate removed, a little bit of dissolved solids to achieve a water quality that matches up with the river. So essentially you have 2 alternatives here, the last one being a river water system that would produce the same water quality, one using the well water and the other using the surface water. So the last alternative is to take the river water and just remove the small amount of turbidity that's there through a filtration process and then bring it out to the distribution system. Okay? So what is that? That is different from this first alternative in that this water will have a lower dissolved solids, lower hardness, and no manganese in it. Okay? Because there are 2 sites at which each of these 3 different processes could be developed, there were essentially 6 alternatives. 3 treatment processes or 3 treatment alternatives at 2 different sites. Okay? Our team's job was to evaluate the costs of those alternatives. And we look at this like the cost of you owning a vehicle. You buy it, new or perhaps newly used, new to you. And then over time, you do maintenance on that vehicle, so there's costs associated with the maintenance as well as the initial purchase cost. And at the end, it might have a trade-in value. We call that a salvage value. And in order to compare all of these against each other, we have to convert all of those costs to what we call a present value. It's called a present value cost analysis. And it enables us to compare all the alternatives on an apples-to-apples basis. Some alternatives may have a higher construction cost, but a lower operation and maintenance cost, right? And so you have to be able to compare that against an alternative that has a low construction cost, but a really high operation and maintenance cost to find out what your real costs will be over time. So that's what this was. And in the end, the team went through an evaluation of that cost analysis, but also an evaluation of the pros and cons of each of the alternatives. And this was a fairly extensive workshop that we went through with the City of Pierre folks to have them weigh in on their opinions on the pros and cons of each of these alternatives. And in the end, the team chose alternative number 6 as the recommended alternative, which is to build an 8.8 million gallon water treatment plant at the Steamboat Park site. That is a surface water treatment system using a process called ultrafiltration to remove the particles, organisms, so forth that are in the surface water, disinfect the water, and bring it out into the distribution system. And the present value cost of that's about $37 million. Turns out that that's the construction cost about in that same ballpark as well, around $37 million to build it. And then if you look at the cost over time of maintenance and the salvage value brought back to the present value, it's about $37 million as well. Okay? You might ask, well, what if we don't do anything? What if we continue on with what we have right now? Well, there's costs associated with that. As the city grows, you need more wells to meet the water demands of the community and little treatment facilities associated with that, each well. There's some wells that were recommended to be abandoned because of the bad water quality, so you need additional wells to compensate for those. And then you have to maintain and operate those existing facilities. Actually, the chemical usage, the cost for chemicals, doing treatment that way is actually more than the surface water treatment alternative, just because of the cost of chemicals that are being used to do this. Okay? So all of those are adjusted into looking at the cost of that system. And toward the end, when we look at what the cost will be to you as a consumer, we'll compare this cost against the cost of the recommended alternative. So what does this all look like if you were to move ahead with that surface water treatment alternative? There would be an intake screen submerged in the river north of the railroad bridge with a pipe bringing the water to an intake building that has pumps in it that would take that water and pump it to a water treatment plant located down here in Steamboat Park. There would then be a treated water pipeline that would be connected into the distribution system at strategic locations in order to get that water into the distribution system. And so those were all elements of the total cost of this alternative. The actual screened intake in the river, an intake pumping station, and a water treatment plant. Just to get a feel for what that might look like, the yellow rectangle on here is about the size of the water treatment facility, about 100 by 150 foot building. You can see this is the Discovery Center here. I think it's about 80 by 100 or so. So it's a little bit smaller building. Here's the chamber building right here. Of course, we're much smaller than the Ramcota. And we've just put it on here to represent the size. The actual location of the building could be moved to fit the site, however that all gets designed in place. There'd be parking and a little turnaround associated with the building as well. And so there'd be some additional space, about an acre, little more than an acre, maybe an acre and a half. It's supper time.
Sorry.
That's okay. I know when I'm supposed to stop, right? Okay, notice here there is the river, the road that goes over the river, the bridge, has Dakota Avenue that's an off-ramp right now. And as a part of the construction for the new bridge, that Dakota Avenue is going to go away. It's going to not be, it's going to be not included in the new bridge. And so the new bridge ramp is over on this side. The bridge gets built over here. And so that's another change that's going to happen to Steamboat Park, is that Dakota Avenue ramp goes away. And I mentioned that here in the next slide. That'll be moved. And so you're wondering, well, why put the treatment plant in Steamboat Park? It's really one of the best locations in terms of proximity to the source and the capability to connect into the distribution system from a cost effectiveness standpoint. That off-ramp will be removed. There'll be some space potentially available there to accommodate the treatment plant. But another reason to choose that instead of the Ram Coda is that the Ram Coda really has terrible access to the treatment plant site. Currently, you need to drive through the Ram Coda parking lot to get to that space. And because of the alignment of the bridge, it would be even more difficult to build an off-ramp on that side and to accommodate traffic both ways. And so it's really not a safe way to move supplies and so forth through that parking lot. There's really good access up Dakota Avenue to the potential treatment plant site. Finally, the facilities could be constructed to enhance the park. And we can't emphasize this enough. We'll show some pictures of this here in a second, but we can add in facilities like restroom facilities or landscaping, potentially fountains, artwork. Just the treatment plant architecture itself can be used to blend in with buildings in the area, like the Discovery Center, if that's a desire. And so architecturally and landscaping-wise, and I'll show you some pictures about this in a second, we can enhance the presence of the treatment facility in the park by constructing it properly. This is a treatment plant in Shoreview, Minnesota, that is very similar in size to the treatment facility that would be built here. And the only purpose that I show this is right after construction. You see they've done some minor landscaping here. But to show you that these can be built so they're architecturally fitting in with the surrounding buildings. This one is up in Fargo. This one's actually nearing completion of construction. It is right next to a park in the city of Fargo. And you can see how landscaping is being built into the side of that facility to enable that facility to be essentially a part of the park. It will have a pleasing look to it. Okay, so that's the site. And just as a reminder, that site was chosen because not only was it economical, but it had some safety advantages associated with it in terms of moving to and from the treatment facility, and would have been the lowest cost of the alternatives that were considered in terms of site access. Okay, finally, what's it going to cost? And so, as is the tradition of the community, Brad goes ahead and looks at the impact of rate increases on folks that live in the community, and chooses some of the folks that are on the commission and work inside City Hall. And so this would be the current 2018 rate, the average water rate for the monthly water bill averaged out over a year for these folks, ranging from $26.90 average up to about $70. If we look at the new rate that would be applied, and here we're talking about, well, what is the cost of the facility to build it and to operate and maintain it? So the construction cost is included in this cost factor. That's payment for that construction loan, essentially. And then also payment for daily operation and maintenance. That gets paid for by the people using the water. And so the proposal is to adjust the water rates to enable the costs of water treatment and the costs of the treatment facility to be paid. And so we did a rate evaluation, and using a blend of putting some of the cost on the base charge and some of the cost onto the I guess I call it the variable charge, the cost per amount of gallons being used. The estimated new rate for these folks, this is on a monthly average, is in this range. So what's the difference? Well, the difference is ranging from about $15 a month up to maybe $45 a month on an average basis. So depending upon the water use, your cost is going to vary. If you're, well, I'd say an elderly couple, let's say, that's living in your home, or maybe a single person living in your home that doesn't do a lot of lawn watering, your cost might be in this range right here, the extra cost, maybe $15 a month extra cost. Happen to know that this is a couple living in this house, okay? Whereas if you do a lot of lawn watering, you might be up in this range, additional cost per month on an average basis to maintain that green acreage that you have. So if you average up all of these values, you get about $30 a month over the whole range, which is about $1 a day. And I think that number has been out in some publications and so forth. But that's an average based across the whole range of water usage. Your actual cost is going to depend on your water usage. And we have in the back at the end of this, on the financial table, Gidget is set up with a computer that has your water usage in it. And if you're concerned about what impact this might have on your water bill, she can provide an estimate for you so that you can see what the impact will be on your water bill. The emphasis here is that the impact on you as a user depends upon how much water you use. Also, that number, of course, changes throughout the year. Here we can see these folks' average water use for each month. And so it's the average of those 7 different water users, and this is the monthly average of their water use. Over a year, it's about 1,500 cubic feet per month is their average water use. And again, that average increase for treated water across all of those months would be about $30. And you can see during the summertime when they water, the water bill goes up as a result of accommodating that additional water use. So to summarize that, for a residential customer using approximately 800 cubic feet per month, which is about 6,000 gallons per month, the water bill would increase by about 60 cents per day. On this random user analysis that was supplied by the community, by the folks at City Hall, that water average of those uses is about $1 per day. And your question is, well, what if we don't do anything? Well, you still have to add those additional wells as time goes on and so forth. And so, and do enhancements and fixes to existing facilities and so forth. And we estimated that in order to accommodate that over the time period of this as well, your water bill would increase between 15 to 25 cents per day as time goes on. Okay? So we're looking at under a no action alternative, which simply means continuing going on with the existing approach. You still need to make improvements to the system, somewhere, let's just say 20 cents per day. If you add treatment, a lower end user might be in that range of 50 to 60 cents per day, or an average across the community, an average of those users in the City Hall example, about $1 per day. You understand that the amount you're actually going to need to pay depends upon how much water you use. Okay? So then the question is, well, what does that look like compared to other community systems? Well, this is Pierre's current monthly water bill, assuming 6,000 gallons of water use per month. It's about $32.25 per month. If you would do treatment with the proposed rate increase, and this is estimated, it'd be about $51 per month. That difference is about $19. That's on the basis of about 6,000 gallons or 800 cubic feet per month. What are some other communities look like? Well, here's an average bill for Brookings, about $37.60. Harrisburg, $46.20. Yankton, $55 a month. Yankton is under construction to add their treatment plant in their system, and so they've made adjustments of their water rates to get to where they are today. Their treatment plant is nearing completion right now. So if you would look at a community about the size of Pierre that's moved forward with treatment and looked at where they would compare to the city of Pierre, it's about in the same ballpark. One more illustration to show how communities compare with each other. What I did was take that average group, the City Hall group, and applied their water use to the rates from other communities. So the blue is Sioux Falls, the orange is Brookings, the gray is Yankton, and the yellow is Pierre on the new rate. So Brookings and Yankton are nearly the same size as Pierre. Brookings a little larger. Sioux Falls is much bigger. The larger the community, the more they reap the benefits of an economy of scale. So the cost per user gets less. But you can see during the summertime that all of those systems have peaks representing that lawn watering condition that occurs in those communities. During the wintertime, they're down here in this rate range. And you can see that Yankton, which is in the gray, and Pierre would compete with each other in terms of what that rate might be. The point is that implementing this is not going to cause Pierre's water to be unusual relative to other communities that have a similar water quality to what Pierre would have. Okay? Okay, so we're right down here to the end. Now, what are the benefits of that treated water? Well, it would eliminate the discoloration. We wouldn't have the issues with brown sidewalks and brown laundry and other water treatment issues associated with manganese in the water. This water would also meet potential future manganese regulation. We don't know the fate of the regulatory progress that's going to go on. And so there's a high likelihood that this water would meet the future manganese regulations. The water would be softer, about 30% less hardness in it, which would reduce your salt consumption by about 30%. If your water softener is salt regeneration is regulated by the amount of water that's used and the hardness of the water. And then finally, you'd have better water quality, a lower dissolved solids concentration and a lower sulfate concentration. We talked about the benefits of that a little bit earlier. Continuing on, less water would be used by the community for main flushing. Right now, the community responds to colored water complaints and flushes the system on a routine basis. Well, if that deposit isn't going to be put into the system, then there would be less flushing required as the system would continue to use this better water. There would be decreased water main deposit buildup. Right now, the deposits build up inside the water main, and they decrease the size of that water main. So eventually, as time goes on, the effective size and flow carrying capacity of the water mains in town are decreased. And by providing better water, that issue goes away. And then finally, this water would be less corrosive or encrusting of plumbing fixtures and appliances. It's pretty routine to replace faucets in this community when you use the city water directly, and replace water heaters and so forth. And so there would be less of that because the water would be less aggressive toward those plumbing fixtures. And then finally, there would be better water distributed throughout the community for some of the commercial establishments and the swimming pool, including, I guess there's an initiative going on to look at a new municipal pool. And the treatment of water associated with that pool would be less expensive as compared to what it would be if the city continued on the way it is. Okay? So that's the presentation. I'd like to open it up for questions, and Brad, if you'd come up and be the facilitator, I'd appreciate it. After the questions are over, in fact, you might ask the question of whether or not you want to ask questions as a group or want to do it individually. Okay, we're going to go with the big group. But there are going to be stations around the room. There's a general question station there, and then a financial station where the computer's at for you to check out your water bill. A location station back there by the mayor. Then up here will be the water quality station. I'll be up here to answer questions on water quality. After the large group question and answer session is over, if you have additional questions that you might want to ask, feel free to come to any of these stations and ask those questions. Thank you.
Thank you
as
very
these have
much.
gone along, the presentation got longer and longer. Some of you have been to all of the ones, and the first one's pretty short. And then as questions were asked, it was determined to include some of that information in the presentation so they get a little bit longer. So I apologize to getting you past what your target was for
Thank you very
the
much.
deadline.
I'm Brad Palmer, the Utilities Director for the city. And so generally what we've done in the last meetings is we open it up to questions from the group. It's your meeting. We'll go as long as you want to. We'll answer every question. We have folks from our engineering department, from our finance department. AE2S is here, so we feel like we've got all the bases covered. We just ask that the questions center around water treatment. You know, I know people have maybe questions on their wastewater bill or their electric bill, but this meeting's for water and water treatment. So if you have questions about those other items, we'll certainly talk with you after the meeting.